Okay, so let me move on to corrective actions. So preventing fluid elastic instability, we've talked quite a bit about the role at 100% power, the velocity of the fluid, that's what transfers the energy to the tube. We've also talked about you need to improve tube damping. And this is a function, here's where the support structure comes into play. So this is a function of the dryness of the steam around the tubes and the supports. And the fluid, if you will, the water-steam mixture dampens in a couple ways. One is just physically the tube, if it's moving through an area of steam that has largely water, a low void fraction, is damped more effectively from physical motion than through a very dry area of very dry steam with very little moisture. Secondly, the more moisture, lower void fraction, you have a film of water between the tube and the support. Even if there isn't a strong contact force, that very film of water with the tube moving across the support provides damping. So that's the role of the damper. So in my second bullet there, the fluid interaction with the tube, it's a function of void fraction or steam quality, how dry the steam is. So as we look at then how to prevent this from Unit 3 phenomena from occurring in Unit 2, it's a matter we need to reduce the velocity, we need to reduce or improve the void fraction and steam quality, which results in improvement in tube damping. So the sum total of that, it's less energy input in the tube, causing the tube to start to move, and is better damping that prevents the tube from vibrating excessively. So let me show you very specifically. I'm going to start with void fraction, then I'm going to move on to velocity. So this chart, this is actual data out of Unit 3. See, the blue bar is the number 3 Echo 88 steam generator, and the yellow bar is the 3 Echo 89. On my graph here, at the bottom is maximum void fraction. So the higher numbers mean very dry steam. So I talk void fraction or steam quality, calculated a little differently, but either one is a measure of how dry the steam is. On the vertical axis, the number of tubes that were actually damaged due to tube-to-tube wear in Unit 3. You can see that all the tubes that experienced tube-to-tube wear damage were above 99% or 0.99 void fraction. This area, very high void fraction, very dry steam, very little water. If I then look at the effective power level, and this is all at 100% power. If I look at power level, I took a little different look at this. So on my horizontal axis, it's the same maximum void fraction. And on the vertical axis, it's the percent of tubes exposed to that high void fraction. And my green line on the graph is at 100% power. What this tells me, that peak there on the far right on that green line, slightly over 30% of the tubes at 100% power were exposed to a 99% void fraction or higher. So that adverse, very high void fraction, the number of tubes in the Unit 3 steam generator is exposed to that void fraction.
Tom, you mentioned that this is the thermohydraulic phenomena, and all 4 generators are designed the same. Wouldn't this not be representative also of the void fraction for Unit 2 at 100%?
Yes, it is.
Okay.
In fact, this graph is very representative of Unit 2. Let me back up. The tube damage, this is Unit 3 specifically. Right. Okay. This graph is identical essentially for Unit 3 or Unit 2 because they're the same design, same construction, the thermohydraulics are the same, which is why early on we concluded Unit 2 is susceptible to phenomena. The yellow line on this graph shows you the effect of reducing power to 70%. The effect on void fraction, again, this is what improves the damping and improves the effectiveness of the existing support structure. There will be no tubes, none of the 20,000 tubes in Unit 2 combined 2 steam generators will be exposed above a 92.5% void fraction. That is a significant reduction in the void fraction and the dryness of the steam with that power level reduction.
Tom, for the void fraction as well as the next slide for that you have for velocities, you're going to talk about comparison between some other units at 100% power. I didn't see that in your slides.
Hold that thought for a minute. Let me get through the slides and I'll come back to that. Okay. So the next slide, I put these two together because I want to show you the actual tubes damaged in Unit 3, the yellow and blue bars, the green line, what was exposed at 100% power, and as was noted by Mr. Lance, that green line would be applicable to Unit 2 or Unit 3. And the effect of a reduction of 70% power, no tubes will be exposed to the void fractions that were part of the cause of the fluid elastic instability, the unstable tube vibration, and the tube-to-tube wear. And that void fraction fundamentally improves the damping, which improves the effectiveness of the support structure for damping.
You've said that a number of times, Mr. Holmes. I'm just trying to understand how it proves that. Could you just, big picture, tell us how that's demonstrated, either calculationally, by testing, experiments? I'm just trying to understand it. By the models that you used previously?
In terms
new
of
models?
how the void fraction improvement occurs?
Right, and how how they demonstrate that improves the damping? How is that calculated? And then how does that translate to concluding that there will be no tube-to-tube wear?
Okay. First of all, we've got our actual data measured out of Unit 3 that just relates where the damage occurred to the void fractions. Then, how do we correlate a lower void fraction to better damping? That is done calculationally, and those calculations are based on experimental data. The experimental data you referred to in the 2002-2003 timeframe developed the understanding and the equations that relates things like void fraction and fluid velocity to the amount of damping that occurs, the amount of tube excitation that occurs, that would allow the vibration to occur above a critical level of velocity based on its void fraction. Gives you kind of a complicated answer, but we take this data, we go into the calculations that are based on experimental data.
From what the Canadians did in 2002.
Largely the Canadians in 2002 to 2005. Westinghouse has some experience with this from a testing standpoint as well.
But, and I know you said that you're still looking at why, but it's my understanding, based on what you know now, that this was not considered back at the time the steam generators were designed.
The in-plane vibration was not considered. Okay. Again, the paradigm at the time, not just MHI, was that if you had adequate margin to out-of-plane vibration, which occurs at lower levels of velocity, for example, you would have more than enough margin in-plane vibration. Clearly wrong. History has shown, experience has shown that was not a correct paradigm. There were many years by many manufacturers supporting that paradigm. The data from 2002 timeframe done experimentally, never seen in practice, and again, we've talked to more than one steam generator designer who confirmed that mindset, if you will. But again, to answer your specific question, the calculation of the improvement of damping with void fraction is done calculationally. It's based on experimental data and real systems.
And this was new work, I mean, as it applies to actual steam generators. Was this been done?
Well, the research has been done since 2002. It's
right.
related to steam generators.
Right.
I think you're familiar with Dr. Michelle Pettigrew, who we brought in,
right.
authored a number of that, ran a number of the experiments, working quite a bit with some steam generator manufacturers. So they were looking at U-tube steam generators.
But the work that was done that went into the operational assessment in this regard, but has that ever been used in the design of other operational steam generators?
I can't speak broadly to the design of other operational steam generators. It is certainly probably a first-time use in operational assessments.
So it represents new work.
It represents new work, as well as the operational assessments we did and submitted as part of the college.
I think what's also important to note is that the return of such a large portion of the tubes to this void fraction level, less than 92.5%, as Tom mentioned, that is very benchmarkable to other plants with U-tube steam generators. Other plants we know operate above 90% void fraction, but less than 95% void fraction, and operate there successfully. So it is backed up by other industry experience from the last several years.
Yeah, I was going to get to that was the heart of Mr. Werner's question in terms of it. So as I get through the next couple of slides, we'll come back to that. What I want to show you, now this shows you a different look at void fraction. In this case, steam quality. The terms are similar. On the left, you see the analysis that shows steam quality, and the red and pink is very severe numbers, relates to high void fractions. This is a cross-section of the steam generators. And on the right side, I show you the analysis at 70% power. You see the blues and greens, which are much lower steam quality values, and they correlate with a reduction in void fraction. I just used the plot for steam quality in this case. If I look at the next slide, I've talked about velocity and void fraction or steam quality is important. This is the look at velocity. Again, at 100%, these are the velocities that occur, and you can see the red and pink, which are the severe numbers, the high velocities. The reduction of 70% significantly reduces the velocity, and again, imparts significantly less energy to the tube.
Tom, can you just describe how those graphs were created, what model was used for these
They're
graphs?
created out of Athos. So the thermal hydraulic model out of Athos, which we are using currently, which we had run by multiple vendors to ensure the results correlate, that's based on today's Athos calculation
Thank you.
for steam quality and for velocity. So now to come back to Mr. Werner's question about, how does this compare? I think essentially that was the heart of the question. At 100% power, the Songs Unit 3 replacement steam generators and Unit 2 is the same basic thermal hydraulics, certainly from a void fraction standpoint, operated in a range of 99.5% higher than other steam generators had typically operated. There had been some in the higher void fraction ranges, as Pete said, but none as high that we're aware of as 99.5%. So clearly, when this design was developed and upsized, we wound up with a void fraction and velocities higher than had been successfully experienced before. Partly because of the underprediction of Fit 3, it was now recognized the lack of margin it created. Okay? And that is essentially part of what drove the damage in Unit 3 steam generators, coupled with the support structure inadequacy. A reduction of 70% power brings the thermal hydraulics, the void fraction or steam quality velocities, back within the range that other large U-tube steam generators have operated with successfully. And we benchmarked that with some other plants through the Electric Power Research Institute.
So what is that value you're looking for the other large steam generators for other units as far as void fraction?
I think we've seen numbers around 95% for a maximum void fraction.
Yeah, in the 90-95% range, and we've got the specifics in the confirmatory action letter response, but roughly in that, other combustion engineering design or modeled pressurized water reactors, those steam generators operate in that 92-94%.
Yeah.
And just so we're clear, we're talking about local maximum void fraction.
We're talking about local maximum
Not
void
average.
fraction. This is a very localized phenomenon. It's not an average void fraction. It's a localized maximum void fraction, which is your most severe condition. And as Pete said, in the confirmatory action letter response, we've got what's called a spider diagram that shows you at 100% power our operating thermal hydraulic parameters compared to several other plants, and shows you the reduction of 70% brings us back in with the envelope of successful operating experience. And I can take you through the Cal response to show you specifically where that is. And that is thoroughly discussed.
Mr. Palmazan, I wanted to question you. Earlier, when you talked about the causes, you indicate that both the high void fraction as well as the high velocities. What I'm seeing that you're focusing on is primarily the void fraction. Is that the main contributor to that, to FEI, or do you have to have both, or can you explain the relationship?
Well, we're focusing on both velocity and void fraction. They're both important. Again, velocity is what excites or puts the energy into the tube. Void fraction is what affects the damping, both by the fluid itself and by the interaction with the fluid and the antivibration. So velocity is important to how much energy you put into the tube, and void fraction is important to how much damping the tube experiences. So I've talked about void fraction a couple times because it's related to adverse thermal hydraulics, but affects the effectiveness of the support structure. So basically think adverse thermal hydraulics, ineffective support structure. By reducing power, I reduce velocity, and I reduce void fraction. Both are important. Okay? Without putting the equations up, velocity itself relates to hyperdynamic pressure, and in that calculation, velocity is mathematically squared. So velocity has a very dominant effect on the calculation of tube instability. So the bottom line here is they're both important, they both have to be dealt with. And the 70% power reduction deals with it.
So, and when you did the comparisons to other plants in the conditions that were operating successfully, you looked at your comparisons for both
Yes.
velocities and void fractions?
Yes, we did, and again, that's fully described in the Cal responses.
Just so we're clear, I mean, so the under prediction of the velocity by, by Fit 3 was not recognized, the problem with the model, when it was changed from square pitch to triangular pitch a number of years ago. But the void fraction, even under Fit 3, while not predicting 99.6%, was predicting 95%, which was still high.
Correct.
And was a matter of concern back in the 2005 timeframe. So I know that's still being looked at, but that was a matter of concern. A number of feasibility studies were conducted to try to lower that void fraction before the steam generators were fabricated. But apparently it was not. So we'll need to understand that better as we go forward.
And we have as well. We've asked MHI for a better explanation of that, and we're looking at it ourselves, because if you say the void fraction was high, it was not predicted as high as 99.5%, but it was high, it was questioned. Ultimately, the calculations and the operating experience showed even with that void fraction, the system should have been effective, and it was not. So clearly that's a failure, several reasons for that failure that have to be dealt with. Okay, operational assessment. So we've built through to how the tubes are moving, why they're vibrating, the fluid elastic instability, the role of the thermal hydraulics, the role of the damping, the role of the support structure. So, and we're going to talk about corrective actions in a minute, but for the steam generator program, as we get ready to return the steam generator to service after any outage with any inspection, we have to do an operational assessment. Early on tonight, I talked about the backward look, the condition monitoring look to say, did the tubes meet their criteria? Before we restart the plant, we've now got to look forward and say, will the tubes meet their criteria with what I've learned about any wear phenomena or corrosion phenomena as I get ready for the next operating period. So that's the operational assessment. Typically, you do one operational assessment. And there's some standard methodology. There's a couple choices on methodology under the upgrade steam generator program. So as we looked at this, we decided, number one, the typical upgrade program would suffice for the normal random wear we saw, the tube to AVB wear. It would not suffice for the tube to tube wear. The tube to tube wear was a new phenomenon. There was really no specific experience with it, with this fluid elastic instability with in-plane vibration. So we simply couldn't do a typical operational assessment. So we really did three different assessments using diverse methods. Okay? And I'm going to start from the simple. We did a traditional operational assessment treating tube-to-tube wear as a predictable phenomenon. And my third bullet, I'll give you, summarizes the result. So we did that. We said that is not sufficient for us. That doesn't give us adequate assurance. It doesn't give us sufficient margin in our minds. So we commissioned Westinghouse to come in entirely independently, no recent history with MHI or our steam generators, and do an operational assessment with their methodology. And they have a lot of experience successfully designing, building, and maintaining steam generators. The third piece, which is probably the most significant and most unique piece, we commissioned Ariba to do an operational assessment. And there were two parts to their conclusion.
Hey, Tom, I'm sorry to interrupt. I just want to make sure it's clear what a traditional operational assessment is, right? You do your condition monitoring, you see what wear is on all the tubes, and then you say for this type of wear mechanism, which we know and we can predict the wear rate.
Correct.
Each of these tubes worn so much they can last so long before you exceed criteria. Right.
Thank you. That is correct. Say a traditional operational assessment would have a known wear phenomenon, a predictable wear rate that I can say over the next 22 months, if it continues, no tubes would wear to an acceptable level and challenge steam generator tube integrity.
Right. So
that's based not only by the plant's experience, but by a database of industry experience.
Right. So that's a typical operational assessment that you would normally perform.
And which we did. But we recognized that tube-to-tube wear, it really did not have any operating experience and was a new phenomenon and couldn't be simply predicted in the traditional way, which is why we commissioned three different approaches to an operational assessment. With Ariba, we took two approaches. We did a very sophisticated approach, and Mr. Howell, this gets to this whole discussion of contact force and gaps between tubes and anti-vibration bars, recognizing that the support structure is an important part of damping and restraining the tubes. So we've spent an extensive amount of time with our eddy current data and further testing, identifying contact points between tubes and anti-vibration bars in Unit 2, statistically calculating contact forces across 10,000 tubes and all the anti-vibration bars, 12 contact points on each tube from anti-vibration bars, and then determining, based on the measured data in Unit 2, a statistical analysis of contact force, and we then applied that to say, you know, out of 12 contact points, if 4 are effectively in contact, it sufficiently dampens and restrains the tube. And that is fully described in the Cal response in quite a bit of detail. So that's one approach, and that approach, we set a stability ratio target of 0.75, not 1.0, but 0.75. We did that specifically to make sure we critically and conservatively modeled that steam generator tube bundle and the contact force and the effectiveness of the support structure, and had margin to fluid elastic instability occur.
So I've read the 60-page summary, and of course it makes reference to the OAs that are this thick, and I haven't gotten through all those, but I will. But this also represents new work, is that?
This is unique. This represents new work, which again is one reason we did 3 diverse methods, because we recognize that this is a significant new body of work, a new approach to this issue, and we know this is something your staff will take some time to understand, and we are prepared to bring in not only our team, but AREVA and MHI to explain the results here. We also challenged this critically. Pete and I have both alluded to these experts we brought in. We set up what we call expert panels. We had multiple challenges all along the way, starting with the concept, starting with is this the phenomena and why, starting with the approach analytically to model this and determine what's acceptable. So we used this panel, including Dr. Michelle Pettigrew, who did all the research on the phenomena, to help us ensure we not only both understood it, but our analysis was an appropriate way to model this and deal with this.
That would suggest to me, not knowing all the details at this point, that there's still a reliance on contact, at least to some degree, between the ADBs and the tubes, so that the natural frequency of the tubes in the inclining direction is improved. Is that?
That is true. The operational assessment with a 0.75 stability ratio limit relies on some contact and contact force between anti-vibration bars and tubes. And again, that's fully described as you talk in the 60-page summary and all the supporting documents. The other thing we had AREVA do is we learned more about the stability ratio calculations. We said if we had no supports effective, none of the anti-vibration bars had any damping contribution, what would the stability ratios be? And for Unit 2 at 70% power, the stability ratios in that worst case assumption are less than 1.
So they actually did 2 assessments.
AREVA did 2 assessments effectively. Now, we weren't satisfied with the stability ratio 1, which is why we continued on with the more sophisticated, detailed analysis showing a stability ratio of 0.75.
So was it like barely less than 1, or?
I'd have to check on the highest value. Again, that's documented in our Cal response. It seems to me it was in the 0.88 range, but I would have to look that up specifically.
Is that in the Cal?
It's in the Cal response, yeah. This is all thoroughly documented and described and discussed in the Cal response. And we'll be glad to get into much more detail with that.
Yeah, I think it's important to point out, we've been talking about, stability ratios of, first off, what's the stability ratio? We talked about stability ratios of 1.0, we talked about stability ratios of 0.75. Stability ratio is a ratio of velocities. The critical velocity is the denominator, and then the modeled or calculated velocity in the numerator. So calculated over critical. Setting a criteria that we would only operate the plant in a condition with a 0.75 stability ratio actually puts in essence, 25% safety margin into your conclusion or into your calculation. So that's the difference between a 1.0 stability ratio and a 0.75. Traditionally, steam generators are designed originally coming out of the factory where you won't see tubes in conditions at greater than 0.75 stability ratio. We do know through industry practice and industry knowledge that as tube wear occurs, right, that those stability ratios can move up slightly, right? So that's why we took a look at the 1.0 stability ratio. So, some of that's influenced by the contact force and other issues associated with the steam generator. So, just wanted to point out more for the audience specifically, we kind of fast and loose here on 0.75 versus 1.0 stability ratio. I wanted to make sure people understood what we were talking about.
Thank you.
Thanks. That's great. So that would, just so I'm clear, but that's the whole purpose of calculating that stability ratio is to feed into the downstream models to calculate whether or not you have FEI in the outplane direction. So does the Ariba work, the new work also have new work that calculates a methodology for in-plane vibration determination.
The stability ratio is calculated for the restart of Unit 2 model in-plane vibration, not just out-of-plane vibration. So, you know, by modifying the equation with the appropriate damping factors, we're analyzing against in-plane vibration. Again, one of the big lessons out of this, the old paradigm, and this truly is a paradigm shift in our opinion for the industry. The paradigm that if you had adequate margin out of plane, you were okay with in-plane, we analyzed against stability ratios for in-plane vibration, because that is the underlying phenomenon.
Does the OA go into how this methodology, analytical methodology, based on the testing that was done, how that was qualified, and you said an expert panel, I guess, was involved in?
Yeah, the OA describes both the methodology and how the methodology was validated against measurements in the field.
Yes, and we had, Mr. Howe, we had the Electric Power Research Institute and their thermohydraulic experts, as well as contracted thermohydraulic experts through the Electric Power Research Institute, come in to challenge those operational assessments and their conclusions as well.
And these companies who did the diverse methods challenged each other's work. So we had quite a bit of challenge, but fundamentally that methodology is thoroughly described, including how it was validated.
Okay.
Mr. Thomas, and I just want to, this may be oversimplifying this, but I think if I understand correctly, to clarify, you had essentially four different operational assessments. One of them you called the traditional, the wear rates that you use, though, although you're saying this traditional and it's based upon the wear rates. It's the wear rates in Unit 3 that you used rather than what you had in Unit 2.
Correct.
Right?
We took the severe case, which is Unit 3, which had significant wear after 11 months, and developed a wear rate correlation and applied that to the Unit 2 traditional operational assessment.
The other operational assessments, did they, can you explain, did they use the conditions that you believe were in Unit 3 or that were in Unit 2?
All the operational assessments took Unit 3 data to either develop the operational assessment methodology or to validate. So it's all based, on the Unit 3 experience, and we factored that in, and the vendors factored that into their analysis of Unit 2. We felt the appropriate conservative thing to do, again, Unit 2 being susceptible, clearly a difference because of the support structure effectiveness. We're taking the worst case data on Unit 3 and modeling Unit 2 based on that data.
Was the support structure, though, in those assessments, was that the Unit 2 support structure model, or was it the Unit 3?
The Unit 2 support structure. So again, taking the Unit 3 data for wear and how fast it occurs and everything else we learned from Unit 3, when we do the operational assessment, we did many measurements in Unit 2 to characterize the support structure in terms of what the gaps are between tubes and supports, whether they're in contact, evidence of contact force, and developed a sophisticated statistical model to spread that over 10,000 tubes per steam generator and 12 contact points. So the Unit 2 support structure and tubes are actually modeled in the Ariba probabilistic assessment. The Unit 3 data is used in all the operational assessments in terms of wear rates.
One, maybe not final, but another line of questioning in this regard. So all this work, I mean, was this principally relied upon to demonstrate the acceptability of the Ariba work that operated at 70% power? I mean, I know it's a compilation of the other two, but in principle.
Principally the Ariba work. And two aspects to Ariba, one with a stability ratio of 0.75 and one with a stability ratio of 1.0, coupled with a 70% power.
So given that, I mean, do you ever consider that a design change?
Well, I think if you think about the principle of an operational assessment, right? The principle of an operational assessment is to take known conditions either at your plant or at other plants, at other similarly designed and operating steam generators, and apply the wear rates seen in those steam generators to your conditions and predict the future, predict your operating period. So it's not a design change. The operational assessment process is intended, as the Steam Generator Management Program is developed through Electric Power Research Institute with NRC's involvement and endorsement, is that it is the forward-looking probabilistic evaluation of what is the maximum safe operating period based solely on steam generator wear. So in essence, it is a prediction, right? A prediction of what's going to occur in the next operating period. So interestingly enough, you know, and as we approach this, as Tom mentioned, the AREVA work is the backbone, operational assessment. But then we said, what if we're wrong? What if fluid elastic instability in plane begins in Unit 2 on day 1 of operation at the same rates it's been occurring on Unit 3? How long can the unit operate before a tube integrity issue becomes a concern? And that was the approach that we had a company by the name of Aptec take. The conclusions from that probabilistic evaluation, which again is very much in line with conventional operational assessment approaches, is that, you know, what we mentioned in the last bullet on this slide that's up on the page is that these operational assessment predictions all show safe operating periods in the 16 to 18 month range. Now, when we applied the additional 25% conservatism on the 0.75 stability ratio, it brought that predicted accepted time frame down into the 8-month period, recognizing that there's still 25% safety margin in that conclusion. Using the operational assessments is what plants in the industry have traditionally used for their proposed operating periods, following the discovery of a condition or a situation within their steam generators. That is the basis of the U.S. nuclear industry steam generator management program. Many plants in the past, in finding new situations or new occurrences in their steam generator, as the NRC, as you gentlemen are aware, have used the operational assessment process to predict safe operating periods. And then you go back into another period of inspection. The intention is to confirm the predictions of your operational assessments. In our cases, not trying to steal some of Tom's thunder here, but the last 2 bullets on this slide talk about that those operational assessment techniques predicted safe operating periods with conservatism and margin in the 16 to 18 month time period. Our proposed operating period is 5 months, right? So roughly 3 times or a third of what the safe predicted operating period is. And then we'll go back in and conduct a whole nother round of inspections to validate and confirm our conclusions and confirm the information that our operational assessments have predicted.
Thank you for that. And I understand that point of view, but I guess another point of view, and I'm not saying this is the agency view, is that, you know, the anti-vibration bars were specifically designed to prevent FEI in the out-of-plane direction. Under the AREVA work, from one point of view is that they're now being used to prevent FEI in the in-plane and out-of-plane direction, which is a new design function, some would argue. And so the question then becomes, how is that treated under design processes, and how does that apply to the applicable NRC regulations that govern design?
I understand the line of thinking and understand that's, as you said, that's not necessarily the agency position, but the anti-vibration bars are designed to prevent excessive vibration, out-of-plane FEI, and at least by experience, also suffice to prevent in-plane FEI.
That's right.
By operational experience, I grant you.
Yeah, so it's not, in that sense, a change in design function.
All right, something we'll have to look at.
Yeah, we understand, and we're looking forward to having that dialogue. As Pete has summarized, the operational assessments conclude at 70% power, an acceptable operating period of 16 to 18 months prior to the next inspection, even with the very conservative 0.75 stability ratio, and there's more margin beyond the 25% that implies, a minimum of an 8-month period prior to the next inspection. Our proposed corrective action is to operate for only 5 months prior to shutting down and conducting an inspection, as Pete said, to confirm the effectiveness of our actions.
Tom, just to belabor this a little bit more, you did 4 operational assessments. One was traditional, and the other ones used some statistical analysis, some different assumptions. Can you describe in layman's terms the operational assessment that you actually used, what you compiled together, kind of the assumptions, basis of that?
Fundamentally, again, it's all thoroughly described in the Cal submittal. We'll be glad to get into it, but fundamentally, as we've said, the backbone is the AREVA work, and the AREVA work had 2 aspects. One was an assessment of stability ratios crediting no supports, assuming the support structure is not effective at damping, with a stability ratio of 1.0, which demonstrated at 70%, we would have an operating period prior to the next inspection of 16 to 18 months. So the stability ratio calculation is based on the thermal hydraulics principle. Okay?
Essentially, that was saying that you could operate for a period of time without FEI occurring.
Without FEI occurring,
the assumption?
not crediting the anti-vibration bars for any damping.
Okay.
Okay. Then the more sophisticated one, more conservative with 0.75 stability ratio, credited the anti-vibration bars, used that sophisticated statistical analysis based on measured data out of Unit 2 and measured data out of Unit 3 to develop a model over the 10,000 tubes and the 12 contact points per tube. They develop a statistical model of the contact points and contact force and apply that to the FEI calculations, crediting damping and showing we're acceptable under a 0.75 stability ratio, which is conservative for at least an 8-month period before the next.
Okay, just a significant difference from a traditional operation assessment where you would assume a wear rate and the tube would not exceed structural integrity requirements for a certain period. This operational assessment is saying we can operate as long as we do not get the phenomena to occur.
Yeah, this one.
In other words, the unpredictable.
That's a good point. Typically, the criteria in operational assessment is to assure you maintain steam generator integrity and assuming some sort of wear or corrosion phenomena would continue. And frequently treating that statistically, sometimes deterministically. Okay? In this case, we set an even more conservative trigger, in the AREVA work. The assumption is not that FEI occurs and it's okay for 16, 18 months or 8 months. There's a 95% probability that FEI will simply not occur. That's the difference in the criteria I believe you're alluding to. And again, that's fully described in the calcium. And again, we're looking forward to getting into more depth of that with the staff in the subsequent meetings. Now, let me summarize the actions. I've talked quite a bit through the evening about this. Fundamentally, a power reduction of 70%. It significantly reduces fluid velocities. That's where that's less energy causing the tubes to vibrate. It significantly reduces the void fraction or steam quality, which leads to better damping in the support structure. And that power reduction keeps us out of a thermal-hydraulic regimen where fluid elastic instability will occur. Secondly, preventive plugging of tubes. This gets to some of the earlier questions. We looked at Unit 3, where the tube damage occurred. We looked at the thermal-hydraulic calculations, and we said there are X number of tubes that are susceptible at 100% power. We elected to be conservative and add even more margin and plug all those tubes. Even though it's 70%, I can realistically show they're not susceptible, we plug those tubes. And that is fully described in the confirmatory action letter response. Furthermore, we're proposing a 5-month operating window prior to the next shutdown and inspection. Significantly shorter than our analysis would support. We feel that's an appropriate, conservative decision based on adequate safety margin. And we'll do 100% tube inspection and repeat all the work we've done during that mid-cycle outage. So to summarize, as you think about this, the power reduction takes us out of the regime where fluid elastic instability would occur with significant margin. The preventive plugging of tubes adds even more margin. That I took tubes that would be susceptible to 100%, I took those out of service. And thirdly, a relatively short operating window, virtually a third of what could be justified by analysis.
I just want one clarification. I just want to make sure there's something that Ryan had said in an answer you've given that I'm not sure if I heard it all correctly. You're saying here that this power reduction is preventing fluid elastic instability, and I thought I had heard before that there was a time period, basically, that it would prevent fluid elastic instability for a certain time period from occurring. Is it always prevented at 70%? Is that what you're saying, or is it prevented for the time period that you're proposing?
In one of the calculations, the statistical approach we used with AREVA, when we set the conservative 0.75 stability ratio, the criteria we set was not tube wear and tube integrity. It was much more conservative. We said no more than a 5% chance of FEI occurring. So the analysis shows that for up to an 8-month period at 70% power, FEI would not occur. Now, with further work and further analysis, we're confident we can extend that. This is a very conservative look at this, a very conservative analysis, which quite frankly is appropriate given the uniqueness of this phenomenon in the first time occurrence of it. Does that answer your question?
I think so. So it's still, the probability of FEI occurring it's not going to occur within the 8-month period, is what you're saying?
That is correct.
But it could occur after that time period?
Here again, from a very conservative standpoint, what we assumed was at the start of the operating period, the support structure we analyzed with the statistical analysis provides certain support, certain damage. Just through normal wear, we're assuming some of those supports can become ineffective over an operating period. So we treated that statistically to say at what point potentially would enough supports become ineffective due to normal wear that would get us too close to a margin issue of fluid elastic instability. And we capped the operating period based on that.
So the fluid velocities and the void fractions would stay the same?
Correct.
That wouldn't change at the 17th, regardless of how long you're operating. It's just the support structure that's wearing and then allowing the tubes to start
Wearing and becoming, say, less effective at providing damage. And that was a very conservative assumption, but we felt that was very appropriate at this point.
All right, thank you.
To summarize some additional confirmatory action letter response actions, we were very, our equipment responded well, our operators responded well to the leak. We looked at our ability to detect even more minor leakage, given the significance of this, and we've improved our ability to detect minor primary or secondary leakage. We've established more restrictive limits than existed previously, and again, we ramped the plant down and took the plant off very quickly, but we now have more restrictive limits in place. We've enhanced the radiation monitors even further on the secondary system, and we've upgraded the vibration monitoring instrumentation around the outside of the steam generators to allow us to gather more data as we get ready to return to service at 70% power to further better understand the condition of the steam generators.
I've got a couple of questions on this slide. Can you kind of compare and contrast your detection capability between previously and now as far as the difference, the delta?
Doug, would you like to step in?
I sure will. When the leak occurred on Unit 3 on January 31st, the maximum leakage was about 80 gallons per day. Our system's alarmed at 30 gallons per day. And as Tom indicated, we safely shut down Unit 3, did a rapid down power. The operators responded properly, the systems responded properly. We have implemented several different methods to improve our leakage detection capability. Without getting too technical, one method is we're using what's called N16, nitrogen 16 monitors on the main steam line headers. Those monitors have a lower threshold of about 5 gallons per day. We've also improved our system response by injecting an inert gas called argon 40. Argon 40 in the reactor coolant system becomes argon 41 over time, and that, if you have a leak, using your off-gas system, the argon 41 is more easily detected by the system, and so your detectors become more sensitive, and we calibrate to that. So using the improved sensitivity, we've been able to go back and look at our operating response and our procedures and improve those procedures such that right now, if we have a leak, and it's a sustained leak of 5 gallons per day at the lower threshold, we will perform a normal shutdown. And so we've made those changes to improve our sensitivity. We've changed and improved the procedures, and we've also tested and run those procedures on our simulator with all of our operating crews.
So the procedures have been changed to, so 5 gallons per day would be a shutdown versus like a night order, which would be a temporary?
That's correct. The actual, it's called an abnormal operating procedure, AOI as the operators call it. That procedure has been changed for the 5 gallons per day lower threshold, and the operators have been trained on it.
All right, thank you. And then for the tube bundle detection, you talk about your additional sensor. The question I have here is, how has that detector, especially in the upper bundle, been verified or to show that it could potentially pick up?
When I'm talking about, when you're talking about the additional vibration monitor we put at the tube sheet and up near the top tube support plate to better collect data related to what vibration might be going on inside the steam generator. As you're probably aware, these sensors are mounted on the shell of the steam generator. To test those and calibrate those with the plant shut down, we open the steam generator and use a calibrated impact camera to see if a certain impact occurring between on the tube support plate is transmitted to the accelerometer pickup and detected. And that's how we tested it and calibrated it. to give us some better indication of what is occurring inside the studio.
All right, thank you.
Thank you.
Hey, Tom, just one more question. A couple of components left in place. You've got the, you're going to have the vibration monitors and the enhanced radiation monitoring system. So some components, if those components become, they need maintenance, they break, what kind of commitments have you made to repair those in a certain amount of time? Treating them like any other piece of equipment that's covered in your tech specs or
Well, as you know, they're not tech spec required equipment.
Correct, that's why I asked the question.
From that standpoint, the key issue here in detecting leakage is well covered. The additional vibration monitors will be treated as a high priority piece of critical equipment and repaired in a timely manner.
Yeah, Mr. Lance, the vibration monitor system has actually 4 sensors, 2 different channels in 2 different locations. Tom indicated the ping testing that we did. So there's a redundant sensor on each of the 2 main channels. And although those are in the containment, the sensors during normal operation, at the first opportunity we would have, our procedures would require getting after and fixing the redundant sensor that had come out of service for whatever reason. Now we know that during this first run on Unit 2, using the vibration probes, we intend to collect data. We know that there's background vibration associated with operating the steam generator. So we understand that the primary goal during the first run here is to collect data and understand what those background noise levels are. And then in the future, when we see an anomaly, we'll understand that and be able to compare it against the background data. The radiation monitor system detectors are worked on based on operational priorities. They are not technical specification detectors. There's other backup redundant systems like drawing liquid samples from the steam generators that we can do if we lose a channel. However, there's a high operational priority based on restoring those to service, and before we enter any sort of power operation on Unit 2, we will ensure that all of the radiation monitor channels are in service.
Okay, is that described in the call response also? Reliability of this additional equipment and how it will be maintained and reliable? I don't know if that's in the call response or not.
I don't think how the equipment is maintained is in the CAL response. We have other procedures and operational priorities for doing that, including adding items to our operational focus list that is driven every day out of the plant department.
Okay.
But we'll definitely take a look at that.
Thank you.
Thank you. Okay, conclusions.
I just had one follow-up question. So to understand, so for the new vibration sensors, really don't have any, I say, operational limits associated with it. It's just data collection, and you'll go back and make that during the next operating cycle.
At this point, it's data collection.
All right, thank you.
Okay. Conclusions. First of all, in accordance with the requirements we committed to in the confirmatory action letter, we have performed a thorough investigation to determine the causes of the tube-to-tube wear that occurred in Unit 3. We've determined, again in conformance with the confirmatory action letter, the corrective action to prevent loss of tube integrity in Unit 2. And we've implemented those actions. And those are fully described in the confirmatory action letter response. The corrective actions we've taken and summarized tonight are conservative, and there is considerable safety margin. We've met the requirements of the confirmatory action letter, and the bottom line is, Pete started the meeting, we've taken a very deliberate, conservative approach to the restart of Unit 2 to assure public health and safety. We recognize the significance of the phenomenon in Unit 3, the potential susceptibility of Unit 2, and have been very deliberate and conservative in our approach to the restart of Unit 2. And again, that is well described, and we are looking forward to further dialogue with the staff to explain the basis for that.
I just have one question, Tom. We're going to talk about path forward, next steps in terms of our reviews and future inspections in a few moments. And so this issue obviously will be inspected, but were any of these actions that were taken evaluated under intensive for our 5059?
Oh, we've evaluated all this under 10 CFR 5059, and it is all evaluated and has been done in conformance with NRC requirements.
Thank you.
Okay, let me turn it back to Pete.
Yeah, thank you, Tom. I know we've gone through a very specific and deliberate technical discussion here, and we've talked about a number of things. I'll just bring it back to Southern California Edison's commitment, and that is that we take the safety of the public as well as our employees very, very seriously. And we feel that the technical level in which we've gone to over the last 8 months to fully understand the situation that we have and apply the appropriate and best levels of conservatism and safety margin to our conclusions is absolutely what's proven. We talked about the methodology for the decision-making related to the technical evaluations and the technical challenge, but I'll also share with you that from an executive decision-making standpoint, I mentioned at the beginning that this was a very significant decision for the company and reached the highest levels of the company, including reviews with the board of directors. In the reviews that the executives had, we brought in additional challenge personnel, people with specific experience from within the industry, as well as some of the personnel from MPR who participated in that, and asked them their conclusions on the same issue. So certainly viewed as a very significant decision within the company, and that aligns with our commitment, which is protecting the health and safety of our employees and the public. We recognize that this is a lot to take in on a Friday evening. I do want to share with folks, if we can go to the next slide, that once again, all of our confirmatory action letter information is up on our website. Also, this presentation will go up on our website after this presentation time. On top of that, we have been conducting open house opportunities for members of the public to interface with the members of our steam generator team, with our employees, the folks who have been involved in this analysis. We've already conducted 2 open houses, one in Vista back in October, one in San Clemente here a few nights ago, and we do have one more planned this year in Laguna Hills. And as we go into the first of the year, we will be conducting additional open houses, and we'll make sure that that information is available to the public. We view that transparency and availability of our employees and our information to be very, very important. And we recognize the importance in ensuring that that information is available to the public. So, Mr. Howell, we thank you for the opportunity to present this information tonight, and we'll turn it back over to you.
Thank you, sir. We do have some additional remarks, but given the time, we thought we'd deviate a little bit from the schedule and our plan. We would propose that we go ahead and take our break now and close this part of the meeting, and then we'll finish up with some closing remarks after the Q&A session.
Art, actually, I apologize. We have one final question.
Hey, please, we're still talking up here. That's right, and the purpose of this meeting is for these people to talk. Okay, we're gonna take a break. Okay.
I do have one final question.
We have one final question here. We'll talk to you on the break, ma'am. Yes.
You described in your CAL response for Unit 2, your plan for operation for the 5-month cycle, 70% power. I guess, can you address what your long-term plan beyond that would be, both for Unit 2 as well as Unit 3?
Well, we continue to conduct work using both our own staff as well as Mitsubishi and also the experts that we have assembled. It's our intention to operate Unit 2 safely at 70% power, to confirm the results of our analysis and conclusions, and then continue to look forward to the future as far as what other operational opportunities or considerations need to be considered for units. If we could see both longer periods of operation, based upon a successful period of operation, which we fully anticipate, longer periods of operation, potentially at 70% power, or with additional analysis and confirmation through our inspections, potentially raising the power output, or proposing a raise in power output for Unit 2. So, we want to start with something that we know is safe, that we know has significant amounts of conservatism and safety margin in it, and then we'll move forward as we continue to gain information. And as you know, Mr. Broadus, that's how the industry has approached many elements associated with steam generator issues, from the original detection of cracking to identifying some of the new phenomena and other things within steam generators. Did I answer your question?
Okay, let's take a break. It's 8:30 now. Let's come back. Let's come back in 10 minutes, and then we're going to go for question and answer to all of you. So.